So let's share the screen and get started with debugging on ARCHER2. Okay. Oh, and something else I will quickly note, it's there in the Etherpad, but in case anyone does want to use the reservation for today, it is just the same as the one from yesterday, except this time we will be using a slightly different code, which is the one I'm just putting in the chat at the moment. Okay, and we have this reservation in place until 4 p.m. today, so this should cover the whole course. Okay, let's get going then. So we covered yesterday the development environment on ARCHER2 and also the Slurm job submission system, the scheduler. Today we're going to look instead at how maybe to help solve problems in code. So we're going to look first of all at debugging code, and then after the break we're going to be looking at profiling code. We mentioned this a little earlier on yesterday when we were talking about the software on ARCHER2, but the HP Cray people have provided quite a lot of tools that come as part of the Cray software on ARCHER2. So in terms of debugging tools, I mean, we have all of these. So the one we're going to be mainly talking about today is GDB for HPC. We're actually going to go through an exercise fixing a small MPI program with GDB for HPC. But we do have other tools. Valgrind for HPC allows for memory debugging. You've maybe used both of the sort of GDB and Valgrind before. These are both with the full HPC mean. They're special versions provided by HP Cray to allow debugging for massively parallel applications. We've also got STAT and ATP, which help produce, well, STAT helps show you merge stack traces for parallel applications. ATP's an easy way of getting a stack trace, which you can then look at with STAT if you find a program is crashing for some reason, maybe it's seg faulting. The Cray Comparative Debugger is available. This lets you run two versions of a code. One of them maybe runs correctly and one of them doesn't. It lets you then watch how they execute side by side so you can see the point where they diverge and one of them starts to execute incorrectly. And although we don't have it at the moment, available for users, ARM-DDT, this is part of the ARM Forge package, will be provided on ARCHER2, I think very shortly. I think I mentioned this yesterday. We're in the process of getting this set up, and this also allows for the debugging of parallel applications. Whenever that does become available, that will be documented on the website. Just now, though, as I said, we're going to actually go through an exercise. So we're going to use GDB for HPC, which I actually think is quite a nice little tool for debugging MPI programs. So to do this, we'll need to log on to ARCHER2. I'll work through the steps on the screen, and then at points, when it comes to actually solving the problems, finding out what's wrong with GDB for HPC, we'll switch into exercise mode, and you all can go ahead and try to run the program through GDB for HPC, get to the points where various problems occur, and we'll fix them one by one. So let me drag my terminal across a bit. I hope you can all see what's on the screen. Is that big enough still for everyone? Please say so if it's too small or illegible for any reason. Everything's okay, thanks, Kevin. Okay, in that case, we'll get going. So the first thing we're going to do is we're just going to grab the code itself, which is available from the website hosting the material. So I'm going to change into my work directory. Remember, there are a few ways of doing this. I'm just going to do the sort of slightly laborious typing out the full path to my own work directory, if I can type it, that is. So here I am. And I'm just going to make a new directory. I'll just call it GDB for HPC exercise, which is actually just the same name as the code we're going to get with wget. I'll just copy that command. Remember, we're doing this in the work directory because what we need to do for jobs is run everything, run with everything from work, because the home file systems aren't mounted on the compute nodes. Oops, except I put it in there. Let me just move that into the directory I created. Okay, so there we are. We've got the code, and I'm just going to quickly take a look at it with GDB for HPC, with Vim, GDB for HPC exercise.c. Vim is my text editor of choice. You might use Nano or Emacs or whatever you prefer. But you can see it's a fairly small, only 54 lines in total, MPI program. Does some communication. One of the ranks then sums even numbers between 0 and 20, and then it finalizes. Nothing complicated. However, it does have bugs. That's what we're going to try to fix. So we talked about how we can build everything yesterday using the compiler wrappers. If I do module list, hopefully this won't take long. Okay, that happened pretty quickly, so that's good. You know, we were having those problems with the modules yesterday. I thought earlier on they had not been fixed, but at least at the moment that happened pretty quickly. So this is just the default environment loaded. So we're going to be building just inside plugin of Cray. We'll be using the Cray compilers. So if I use this command here, cc, just means we're going to use the C compiler wrapper to build. -G means we're going to add in the debug information to the executable, and we're actually going to be building GDB for HPC exercise to an executable, which we'll just call GDB exercise. Again, I'm just going to copy that because it will be faster than me typing it and making typos. So there we go, that's built, and we've now got our executable GDB exercise. So I'm going to load GDB for HPC now, and we're going to be running this in parallel. So that means we're going to be launching GDB exercise, the executable, within a parallel job through Slurm. There are a few ways you can do this. I'll talk about some of the other ways at the end. The way I'm going to do this now for this exercise is I'm going to start GDB for HPC, which you just start by typing GDB for HPC. Move this over a little, give you a little more room with the terminal. And you can then launch the debug jobs on Slurm from within GDB for HPC. Oops, except I do need to load the module first. Okay, and then I'll start GDB for HPC. And there we go, and we go to a debug all prompt. So to launch the application, we use the launch command. So this is the command we'll be using roughly. We'll change it a few times as we go through this debugging exercise together. We tell it that we want to launch a job. Then we've got this section here, launcher args, and these options inside the quote marks should look familiar to you. These are all of the options that we were using yesterday to SBatch to tell it how we wanted our job to be run. So again, we're telling it to charge to the TA062, and that's our course, remember, budget. We want to run this, in this case, on the standard partition. This example here is using the short QoS, which, remember, limits the numbers of nodes you can use, and also means you can only run for a maximum of 20 minutes, but it should help you get your jobs running sooner. So good for debug jobs like this. 1 task per node, 1 CPU per task. So this is also going to be using the default of 1 node. exclusive. That isn't really necessary actually, because it's going to be exclusive anyway. And export all tells it to carry through the environment from our current shell through to the job. So if I copy that, and remember as well, if you want to, you could change the QoS to reservation, insert -- reservation, and then put the code in, and that will run it on our reservation for the course instead. And in fact, I'll show you how to do that now. It's fairly simple. Let's just change that QoS. Where is QoS? There it is. So we'll just change the QoS to reservation, and then set the reservation to be, and I'll just copy that straight from the chat to here, like so. And that will start it. While we're waiting for that to start, I'll explain this last part. So after the launcher arguments, we've got this funny looking section of options there. So the second part is fairly obvious what this is doing. This is saying that what we want to launch is GDB exercise, our executable. This part is maybe less obvious. Here what we're doing is we're almost assigning a variable which we're calling myprog to this instance of the run, essentially to this job which we're launching. That means that from now on, inside GDB for HPC, if we want to do anything, if we want to run any commands which refer to this specific instance of our to this specific job that we're launching, we can do it by referring to $my_prog. So, for example, we'll see in a bit, if we wanted to kill this job from within GDB for HPC, we would tell it to kill myprog. And this bit here in the curly brackets means that we're launching with one task. So this one here maps to this one here. We're launching it with one MPI task only. Okay, so I've run that launch, and we've got this output now down here. That's told us it's starting the application, please wait. It creates some communication networks. I believe what's happening under the hood here is that it spawns multiple GDBs for each task and then connects them with with servers. I believe that's what's happening under the hood of GDB for HPC. Some more output, launch complete, and then finally it tells us it's got to an initial breakpoint, and it tells us where that is. It's inside GDB for HPC _exercise.c at line 9. So that's the point where it's got to. It started the run of the executable, and it's paused it at a point matching that line in the initial source code. Something I'll mention just here quickly, it could be relevant. This can take a little while. You saw there it took a few seconds to do that, to start it up. If you launch a job using many tasks, I'll leave it to your imagination what many might be, maybe thousands or tens of thousands, this launch can become actually quite slow. So there are ways to basically make maximum use of your compute time if you want. Again, we'll talk about that just towards the end of this lesson. So at this point, the program has launched, and I'm working against the clock here because I've only got 10 minutes before the job ends. It's still working, and if I have another terminal open, I can run SQ and I'll see this job running. But here we're at a prompt, and now we can give commands to GDB for HPC and tell it what to do now that we're at this point with the execution paused. So I've listed here some of the more useful, I think, commands, certainly not all of them. If you type help, I'll just type help quickly here to show you, there are actually an awful lot of commands, and you can actually go into GDB modes here, which changes everything to work like regular GDB, and then you get even more options. So the most useful ones that we're going to look at just now are list, next, step. We won't need break. We will need halt, and we're also going to use print var, so you can print var to check what some variable is at the point you're at. You can watch a variable so that when it changes, you get a message telling you what it's changing to. Backtrace, quit, kill we'll also use to end these, and release we can also use. Most of these you can also abbreviate, so rather than typing list, so I'll do list now to show you. We were told that the execution of the program had been paused at line 9. If I do list, it will show me the source code at line 9 on for another few lines afterwards. If you do L, that does the same thing as list, except it will now start at line 19 instead. And then I could do L once more, or list, both are the same. I can do backtrace if I were at a point where I wanted to backtrace, or I could also just type BT. So we can then run next. So we're going to move forwards one line. Remember, next takes you to the next step of the program, but doesn't enter any subroutines or functions. We need to use step if we want to actually go into anything which is being called from the current subroutine or function. So we've moved on now to line 13. That makes sense. We were at line 9 before. Now we're at line 13, where we're finding out the rank of this task. And if I do L again for list, we'll see that's where we are. And we can go on, and here we are. We're now at line 15. We'll do list again, and we'll see that we're changing count. That's going from whatever it was initially, whatever it was initialized at, which wasn't specified, but wasn't chosen, and it's now being set to rank +1. So if we print count, we'll see we get some useless number that doesn't really mean anything to us. So what we have now is the first exercise. I hope you've been able to follow along with that. I'd say at this point, let's spend 5 minutes on this exercise. What happens if you keep on using next and list? So if you start your job, start your debugging job from within GDB for HPC, just the way I've done here, and keep on just going through it with next to move to the next line of execution within the main function, and checking the source code with list to see what's happening in the source code itself. I'll give you 5 minutes, so let's come back at 28 past and see what you've managed to find by just moving through the program. I did say that this is bugged at the moment. This program is bugged, so you might see something. It may not be what you're expecting, or it may be blindingly obvious to you. So I'll give you a few minutes. If you're having any trouble in that time getting this to work, just let us know. Hi everyone. So my job ended and then crashed when I tried to start another one. So I'm going to start again, but hopefully that 5 minutes was enough for you to go into GDB for HPC, start your debugging job, and move through it with next until you found something happened. Did anyone manage to do that and get to, I'll call it an event? Input error rank 0. Yes, an event, not a party. No, so if you did this, yes, of course, you would have got through it and you would have just run into an input error. The issue is that we get some code executing which relies on there being 2 tasks rather than 1. We can actually take a look at this if we just take a quick look at the GDB for HPC exercise.c code. we end up with an MPI send going from the rank 0 task to the rank 1 task, and then the rank 1 task is trying to receive, and that's not going to work at all if you've only got one task. So npitch basically crashes out with an error. So this isn't quite a bug to solve, it's just that we're actually running the program wrong. So if you quit GDB for HPC, start it again, and this time we're just going to launch it across 2 tasks rather than 1. So we'll use this command here, like so. And if you press enter, that would then start it. The next exercise, I won't do this because I've only got the 10-minute time limit. I could change that to 20, but I don't want to use up a load in case one of you wants to use it during this exercise. We can see from the code, if you were to look at the Vim, that it tries to be sending, it tries to send count from the one task to the other. So if you run the count, if you run watch count at the GDB for HPC prompt, as you set up here, it will keep track of it and it will print it out whenever it changes value. So you should be able to see when it's set and if the send completes, whether it changes there. So the exercise now, I guess we can expand that, can't we? The exercise now, try doing the same now. Try running it. Keep a watch on the count variable. Carry on through the execution of the program using next and use list to see what code is about to happen. And then see what happens. And maybe more importantly, see if you can see the problem and how to fix it. Again, this could be very obvious to you without even having to use the debugger. But this should give you an idea of how you can use GDB for HPC to do this. So again, this is a little more in depth. So I think we'll leave maybe 8 minutes. We'll get back to this at 10:40 because there's potentially some coding for you to do here. If you think you can do this, see what the problem is in GDB for HPC, and then go out, change the code, and solve the problem. That would be fantastic. If not, don't worry, we'll walk through it as a group once that 8 minutes is up. So we'll come back to this at 10:40. Hi everyone. So hopefully you've all had a chance to try that. I can see in the chat, Williams, I think you've spotted something very important there, I think. So let's take a look at the solution together. So as Williams said, the problem is an MPI issue. So I will actually quit GDB for HPC. Let's take a look at the code. So what you would have found is that around this point here, where I am at the moment, we go into some communications. The rank 0 task you would have found would be trying to send the count variable across to task 1 using a tag of 0, and then it goes into a barrier, which will only pass when the other task also reaches the barrier. Meanwhile, task 1 goes into an MPI receive. Remember, MPI receive is blocking, so it's not going to move on until it's got this message. It's going to receive some integer and put it into count, but it's receiving actually from task 1 with a tag of 1. So this isn't ever going to work. So we need to make a few changes here. So count is being sent, but it's never being received. So instead, let's just make some fixes here. Let's just let's just say, let's make both of the tags 1, and we'll just fix those, we'll fix the direction of the communication, like so. So now we're going to be sending that message with a tag of 1, and it's actually going to go the right way. We're going to send it from 0 to 1, and rank 1 is going to receive it from 0. So that's hopefully our first issue fixed. And of course, as long as rank 1 was here waiting on the MPI receive, rank 0 will have been stuck here on the barrier forever. So we ended up essentially in a deadlock there, with neither task able to move on from what it was expecting the other one to do. So there's one problem fixed. So we can save that and quit. And now we'll rebuild it. So again, just cc-g. Again, we want the G flag so that we get the debug symbols in our executable. Okay, so let's do this section now. So we're going to start up GDB for HPC once more. Let's launch the program again. I'll show you this part. This time I'll just launch it. So this time I'll just launch it on the short QoS rather than on our reservation. But again, I'm going with 2 tasks per node. This should start quickly. The short QoS usually lets things get going immediately, but if it does take a little while, if it does take more than a second, I'll switch to our reservation. Though I think it's okay. So here we are via list where we are, and get going. Let's watch count again. Then we'll just carry on. So remember, you can do next, and you can do list. So here we are. Something else I'll note quickly, something I didn't note before. When it tells you here, myprog 0.113, this is telling you that both processes, both tasks are on line 13. You probably saw that as the 2 ranks diverge in what they're doing, you'll see that this will tell you instead that myprog 0 is on one line and myprog 1 is on another line. We'll just continue onwards. We'll just see everything that we saw before. And again, we can next and list. We get a watch point 1 telling us, watch point 1 variable expression count. It's told us that the count has changed, so we can print count. We get the 2 values on 2 different values on each of the 2 ranks. Let's carry on. Now we're being told that the 2 tasks have diverged. Rank 0 is on line 18, rank 1 is on line 21. Let's list that. And now we can see where the 2 are. So rank 0 is now on that send, except it's now sending with a tag of 1. And rank 1 is now receiving, this time from task 0. Let's see if we can get past it. And we get another watch point 1 variable expression count. If we print count again, myprog 1 no simple count in current context. It should be. Let's go on to the next line. Let's see. And if we list, so 0, of course, so 0 is something right is still not happening. Actually, yes, so we can see here. So myprog 1 is now at line 16? No, it's not. This is the issue. Always live coding, things go wrong. If anyone in the course can see what I've done wrong, please shout and say so. So if I go next. Okay, so what else we can do here? I can show you actually. So we're being told that my prog 0 is actually running at the moment. If I type halt, that will pause it, and now I can get a stack trace to see where they all are. And I will be told that my prog 0 is at line 19 of GDB for HPC exercise, which is still the barrier. And my prog 1 is still waiting at the receive. So did I actually make that fix correctly? Let's quit and take a quick look. 101. So if I vim gdb for HPC exercise.c, I think I've done everything correctly here. What about all of you watching? Maybe you've been able to see what I've done wrong. So at this point, there is a final bug, but it happens later on in this function that we call. Let me try again. Let me quit. Maybe I was doing something wrong in the launch. So let me start. Not in the launch. I'll just call it my prog again. And this time I'm just going to let it continue. So I'm just going to run C, or continue, without any breakpoints. So it's just going to start running, and if nothing goes wrong, it will continue through to the completion of the program. So I'll just run. So C you could do, or else continue. Which point I will list. And we're told the application is running, which is what we would expect. Both tasks are doing something. So I'm going to halt. And now I'm going to do a backtrace for both. So task one's backtrace. Oh, okay, no, so task one is correct. So task one, if I list, oh wait, I might need to go up a long way. So task 0, okay, so that was correct. I think I possibly stepped into something I didn't mean to step into before. So what's happening now is what's happened is that task one, we can actually see the rank 1 task is at line 34. If we keep on going up and up, we can do this a lot. We can actually go, how many frames up is that? 19, 20? Okay. Possibly up too much. The rank 1 task is basically waiting in the MPI finalize. It's got through to the end of the program. It's waiting for the rank 0 task to also reach there so that MPI can be shut down. The rank 0 task, on the other hand, is at line 46, which has been called from line 28. And we can see this here. So there's line 28, the rank 0 task called sum even and went into the sum even function, and it's now here. So it's gone, it started up, it set a variable called result. It's gone into a loop, which is going to carry on running. So now let's take another few minutes. Well, we've kind of gone through it anyway, actually. Having gone through this, I'll say at this point, can any of you now see what the issue is with the code? It looks like the rank 0 task has gone through into sum even and into this loop. And if we start it again, so we can just halt and continue as much as we like. If we halt it again, and then we can see it's again, the rank 0 task is again stopped at line 46. So if I do list again, well, it doesn't work. You can't do it too many times, can you? So let's just quit and take a look at what's happening at line 46 of the code, because we can see that the rank 0 task seems to be getting stuck there. So let's just vim gdb for HPC, exercise.c, and let's go to 46. So this is line 46. It's this if statement checking if I is an even number. So what's the issue here? It's probably very obvious to all of you. If anyone wants to just type in the chat what needs to be done here. So we're inside this loop. As the print statement would be saying, the sum of these even numbers between 0 and 20. So we're going to be looping up until we get to max, where we've set max to 20. And every time that I mod 2 is equal to 0, mod 0, it's a simpler. It's actually an issue with I itself. Yeah, I++ only happens if I is even. It's really the issue is you've got it, Carvana. Yeah, the I++ is just never going to happen. It starts off at 0, and so it's never going to increment. So we basically just need to move it outside of the if so that I can actually increment. So I'll just do this, and I'll just hastily add it in there. Yes. And then if we rebuild that very quickly, I'll start it up. Let's just run it again, same as before. This time, I'm just going to let's see what could we do. We could watch some. Let's watch some. So So sum is the variable containing what's returned from sum even. So let's watch sum. Oh, not in current context. Let's set a breakpoint at line. Let's set a breakpoint at line 27. So let's do GDB for HPC exercise.c at line 27. So we've created a breakpoint, and then I'm going to continue. Both are now here. Both have reached that if statement, if rank equals 0. Okay. Let's carry on. We're now at different lines. Let's see if we can print some now. Oh, next. Print sum. The application is running. Again, live coding. And line 30, what's that line 30? I can't remember what's that line 30. I think I've possibly wrecked it again with my watching of sum. If I release my new prog, here we go, and I'll start it again. So I can call this, I don't know, my second prog, for example. What you can't do is reuse these names within a single GDB for HPC session. Okay, this time I'm just going to continue. I'm just going to try and let it run to completion because we are now at 11 o'clock. And there we go. This time, when I didn't start messing with the variables, we've just reached the end. So at that point, the program is debugged. We fixed those problems, and we could run it as a normal job. So I mean, that's a short example of how to use GDB for HPC to debug applications. Really, most of the useful commands, I think, are on this page, these ones in particular. So that's how you use that tool. There are other ways to do it. So as I said, there are other ways to launch the jobs. The way that way works, where every time I was doing this launcher args, telling it which account to use, partition QoS. As I said, this is launching a new job within Slurm every time that you do it. If you maybe need to launch something big, even if it's only going to run for a while, you might find that for a minute or so, you might find that you have to spend a long time every time that you start it up, waiting for that job to rise to the queue and get going. So an easier way, perhaps, if you find that waiting for each launch takes a long time, an easier way to do it, to cut out some of that time, is to instead launch from within an interactive job. So we talked about running interactive jobs yesterday afternoon. If you were to salloc, run salloc to start an interactive job, again, you would just request which partition to use, which QoS, how many nodes, how many tasks per node, all of the usual information. And then you would have to wait for that job to start. And if you ask for a lot of nodes, you may have to wait for a little while. but then that job will start. You can then load and start GDB for HPC. Then within GDB for HPC, you don't have to do the whole launcher args part because you're already running within a job. You can just say launch and tell it the name for this job that you're launching, the internal GDB for HPC reference to the job, how many tasks you want, and what executable to launch. And that will then start running straight away on the jobs on the nodes which you've already reserved for this job. So if you know that you're going to be starting and stopping jobs and runs of your code within GDB for HPC very often, you may find that an easier way to do things is to salloc a job, get your nodes reserved, and then just start working on those nodes, and you can start and stop the execution of your program inside GDB for HPC as much as you like, as long as your job is still running. I guess the thing to be aware of is that you will be charged for this job, even in the portions of your work when you aren't running something on GDB for HPC. So if you're running on GDB for HPC, quitting, making a quick change to code, then going back to GDB for HPC and starting it again, you would be charged even for those sections of time where you're jumping out to start fixing code. And yes, and you will still have to wait for the servers to start every time. But at least you won't be waiting for the job itself to start every time. Something else that can happen is maybe you are running a regular job and you find that something's not going as you expected. Perhaps it's hanging, something isn't executing as you're expecting. So what you can do in that situation is you can connect GDB for HPC to the job as it's running. So you need to find something here called the job step. So first of all, you'd find your job, the job ID. You'd use SQ if you don't know it at the moment. Then you use a command called sstat on that job ID, and that then tells you all of what are called the job steps. You don't really need to know too much about what that means, but for every srun within a job script, because you can have multiple sruns within a job script, there is a job step. Most jobs which just run a single srun within them will just have a job step of the form job ID.0. Then if there were a second srun, there would be a .1 as well, and so on. Once you know that, you can then start GDB for HPC, then run this different command, attach. You'd still give it a reference, so $myprog, say again, and then you'd give it the job step that you want it to attach to. At that point, you can start doing whatever you need to inside GDB for HPC. And yeah, and if you find you just want to let it start running normally again, or if you do make a mistake and attach the wrong job, you can release $myprog. So that's been a brief 1 hour run through of using GDB for HPC on ARCHER2. We do have more information in the ARCHER2 documentation on using Valgrind and HPC and ATP as well as GDB for HPC. As I say, we've got ArmForge DDT on the way, which will be another tool that has a GUI to go with it to help you debug graphically. Once that's set up and ready for users to make use of an ARCHER2, you can expect documentation to appear there as well. And of course, the Cray technical documentation may also be helpful. Okay, at that point, we've finished. We'll go for a 15-minute break now. So we'll come back at 20 past 11, and at that point, we'll get started looking at profiling tools. Okay, thanks. You're very welcome. I'll see you. I'll still be around through this break. So if anyone has any questions in the meantime, please go ahead. Otherwise, I'll see you all again at 20 past 11.